Hello, chemists. It's Jolly again. This will be the last review on the first semester material. And so we are going to talk about the structure and spectroscopy. All right, so this is the handout that I have, and the answer key is already on Canvas for you. So I'm going to really cruise through a lot of this because a lot of it is really, really, really basic. All right, so don't forget the different hybridization states, sp3, sp2, sp, and then they have their different angles. Okay, so remember 109.5, and we've got 120, we've got 180, and then this one is made of a sigma. This one's a sigma and a pi, and this one is a sigma and two pi's, and pi's are more easily broken. So hybrid orbitals are the overlap of hybrid orbitals. Sorry, the overlap of hybrid orbitals creates a sigma bond, except with hydrogen and helium because they don't hybridize. And hybrid orbitals can also be used to accommodate lone pairs. And the empty p orbitals can be used to make pi bonds, or they can remain empty. All right, here's just a little blurb. Hey, single bonds are the longest at 1.54 angstrom, but they're also the weakest at 350 kilojoules per mole. And then there's a little blurb about double bonds at 120 and the triple bonds. And then here, remember, you should be able to do the type of bond. So single, double, triple, sigmas, pi's, lone pairs, angles, and hybridization. So any molecule, you should be able to do all of those. So we're going to do this one together. All right, so label all the sigma bonds, the pi bonds. So the pi bonds are easy. So anytime it's a multiple bond, even if it's between heteroatoms, that's going to be a pi bond. Change colors. All right, sigma bonds, there's always a sigma bond. So there's a sigma bond in there and there. And remember, that is drawn, so that's a sigma bond too. And remember, there's two hydrogens right there, so they're drawn. And then, of course, whoops, change colors. We'll do green. There's a lone pair and a lone pair. Okay. And then the angles that go along with all of those. And then we learn to do units of unsaturation. The overall idea is 2n plus 2, where n is the number of carbons. That is the maximum number of hydrogens a molecule can have. And anything that is shorter than that, and it usually comes off in twos, is going to give it a unit of unsaturation, which usually implies you either have a ring or a pi bond. So I gave you a few little easy examples right there. What I'm working up to is this isomer page. All right, constitutional or structural isomers. It has the same molecular formula, but it has different connectivity. Where stereoisomers have the same molecular formula, they have different they have the same connectivity. But they have different 3D connections. And then we have learned a few types. So remember, chirality is an entirely different question, but we know structural, which is often cis-trans, EZ, and then we know the, we'll just say with stereocenters. And that is the enantiomers and the diastereomers. All right, so those review questions are for them. And my wonderful little thing, this is on your reference sheet, okay? And then naming was a long time ago, but determine the molecule is chiral, the number of stereo centers, and then also the name. That is a really nice review. All right, and then just a few questions. Hey, can you draw out every different possible type of isomer? And we're just going to do this first one. All right, so the first thing is check its units of unsaturation. So 2 times 4 plus 2, so 8, 9, 10. How many does it have? Okay, it has 9 hydrogens, so we're going to subtract the 9, but remember halogens count as 1, so that is 0. So it has 0 units of unsaturation, so that means it cannot have a pi bond or a ring. Because it has a bromine, that means it is an alkyl bromide. And now we just plug and chug. All right, we have 4 carbons, so I like to keep them in a row. 1, 2, 3, 4. Put bromine on the end. Stay with that theme. Move bromine in. Now, if I move it into this spot, it's going to turn into the same thing. So I've exhausted my 4 carbons, so 3 carbons in a row. Keep the bromine on the end. If I put the carbon right there, it's going to turn back into the one above it. So I'm going to take it one more, and that is unique. And I have used up all of my 3, so then I'm going to move my bromine instead of my carbon. And so there's 1, 2, 3, 4, but don't forget this one right here. That is a squiggle, okay? That is a stereocenter. So there's an R and an S, and so that makes a total of 5. I know that was very fast, but I have handouts with all of the instructions on those specific topics too. And then the curly arrowed notation. But what I really wanted to review is your spectra. All right, so we have the IR spectra, we have the proton NMR, and we have the carbon-13. And then, of course, don't forget the mass spectra. All right, so here are the instructions for the mass, the IR, the proton, and the carbon-13, but we're going to do a question together right there. All right, how are you going to label each one of these? When you're doing an IR, remember you're going to circle anything that indicates a functional group or its parts. So this, okay, that's around 3,400. That is an OH. This nice little oven mitt is your sp3 carbon hydrogen bonds, okay? And then anything past that 1,500. So if you really don't remember, I suggest you go up to my outline and you draw lines at 2,600, 1,900, and 1,500. And remember, anything above 2,600, those are your hydrogens. Anything between 1,900 and 26, those are your triple bonds. Anything between 15 and 19, those are your double bonds. And then anything down here is your single bonds. And we don't use it a lot except for that carbon oxygen. So if you need to still draw those lines, there's nothing wrong with that. Get back to our example. All right, so I would have drawn it about 26, about 19, and right there. Okay, so the only thing I have were hydrogens, and then these are all carbon single bonds. And go back to the same color. Because there is an alcohol in here, remember, the only one that we really find of interest in the fingerprint is that carbon oxygen single bond. All right, how are we going to know what kind of spectra this is? Go back to, let's go blue. All right, we go from 0 to 11 parts per million, and so that is indicative of a proton NMR, and the reference would show up at 0. Okay, this one doesn't specifically have a little reference mark. And the first thing you do is label all of your peaks. And I like to go from left to right or from downfield to upfield. And I tend to use small letters. So A, B, and C. And then either right above those or over to the side, A, you're going to tell me what it is. That is a 1, 2, 3, 4. So that is a quartet that integrates for two hydrogens, and it is found the center, so roughly, I don't know, we'll say 3.7 ppms. This one, B, is a singlet that integrates for one hydrogen, and it looks like about 2.6. And then this one is a triplet that integrates for three hydrogens, and it looks like 1.2. And then you add up all the hydrogens. So there's 2, 3, 4, 5, 6. So I like to put that up here. There are 6 hydrogens. That is an even number, which means it can't contain nitrogens or halogens. And there are 3 peaks, which means there are 3 unique types of hydrogens. All right, that is how you would label the proton NMR, but we can get more from the proton NMR than we can from the IR. So we're now going to start to break that down. All right, a quartet. How can you get a quartet in 3.7? And that's the key right there. 3.7 means it's been really shifted. And so the way you get a quartet is you have to have 3 neighbors. So CH3, and it integrates for 2. So this is the peak. And then it has to be next to something electronegative for it to shift. So that is responsible for A. Now B, how do you get a singlet? Well, you don't have any neighbors or you're a heteroatom. And this one is in 2.6, so that is very indicative of an OH. And then last but not least, how do you get a triplet? You have a CH2 next to you, and it integrates for 3, so you're a CH3, so that's the one. And at 1.2, that's just normal. And so those are all the pieces, and when you are done, you draw the entire structure out, and then you label who goes where. So that one is A, this one is, I said A, that one is B, this one is A, this one is B, and this one is C. And then you check. C, so if you hide this portion right here, it's 1, 2 plus itself, so that should be a triplet that integrates for 1, 2, 3 hydrogens, and it's in the normal area, so about 1 to 2. This one, okay, hide those 2 hydrogens, and it's next to 1, 2, 3. Heteroatoms don't split, so 3 plus itself makes a quartet. Has 2 hydrogens that are being hidden, and it is directly connected to a very electronegative, so it shifts to 3. And then the B is the hydrogen on an oxygen, the heteroatom. It does not split, so you get a singlet that integrates for 1, and it can show up anywhere between 2 and 6, so that's not so helpful. But usually when you get a singlet, it has to be oxygen or nitrogen. Put that B a little bit better. All right, that's how you would label the proton NMR. The carbon-13, remember, doesn't give us as much information. And so I tend to like to not use the same. So label them again, A, B, C, or D. So I used capitals this time, or 1, 2, 3, 4. Just make sure you don't use the same one so it doesn't get confusing. So there are 4 peaks. That means there's 4 unique types of carbons. And then we take a guess at what they could possibly be. All right, this area up here is our carbonyl range. This area around right there is our aromatic. Okay, and again, I'm looking back at that reference sheet with the outline. And so right here is the electronegative. Okay, so R, some kind of Z, and then just down there, that's just the alkyl region. So really not a lot of information from the carbon-13, but it's a great proof. Okay, let's do this entire problem. All right, there's my IR. So this great big thing that goes whomp over my sp3s. This is a COOH. All right, these right here at the bottom that are hiding, remember at 2900, that's my oven mitt, so that's my sp3 carbon hydrogens. Ah, there's the WOMP. That is a carbonyl. And there's there, and there's there. All right, and then down here, there's that CO. But because it was carboxylic acid, it was so obvious that we didn't know it. So this looks like there is some kind of carboxylic acid. All right, for our proton NMR, we have A, we have B, we have C. So we have 3 peaks. And we have 1, 2, 3, 4, 5. We have 6 hydrogens. It's an even number, so you cannot have a nitrogen or a halogen. And A is a singlet that integrates for 1, and it looks like about 11.9. Right off the bat, I know that's the COOH region. All right, my next one, B, looks like a 1, 2, 3, 4. It looks like a quartet that integrates for 2, and it is at about 2.1. Now that is a dead giveaway for a C right next to a carbonyl, and it's integrating for 2. So that's the one we're talking about. And to get a quartet, it would have to have 3 neighbors. So that's what that one looks like. And then C is a kind of ugly, lots of shadow peaks, but that looks like a triplet for 3 hydrogens at, oh, I don't know, 1.1. And the way you can get a triplet is you have to have a CH2 next to you. And in order to integrate for 3, okay, you have to be a CH3. And that's just in the normal alkyl world. So there's my 3 pieces, and then you manipulate them. And there's only one way to manipulate these, and that is CH3, CH2, COH. All right, so A is the carboxylic acid. B is the quartet, and it's shifted. So B are those hydrogens, and then C would be the methyl hydrogens. Oh, look, we didn't even need these 2, but we're still going to label them. All right, this one's going from 0 to 200, so we know that is the carbon 13. And the reference point would be around here, and it would be that little triplet, but a lot of the new carbon 13s don't put that. All right, I'm going to use capital letters, A, B, and C. So there's 3 peaks, which means there's 3 unique types of carbons. This is the carbonyl range. So I'm pretty sure that one's a carbonyl, and these are just in the alkyl range. So from the carbon 13, I can't get much, but because I already did my proton, I know that this is A, and the furthest downfield would be closest to the carbonyl. So this one's B, and that one is C. And this is almost a moot point now, but the mass spec, remember, has the mass to charge ratio and the intensity on the axes. And you go furthest to the right, which would this peak, and then you're looking for the molecular ion peak. You're looking for M+1, and you're looking for M+2. All right, M+1 is in a 1.1% ratio, and M.2 would be the halogen ratios. So 75 could be my peak, but you always go 1 back. And is that a 1.1 ratio? So this peak and this peak, do they look like an M and an M+1 peak? And yes, that looks pretty realistic. So I'm going to label that one was my M. This is my M+1. So there is not an M+2 peak on this, which means my molecular weight is 74 AMU, and it is even. So there is no nitrogen, and there is no M+2. So there is no chlorine or bromine. I know I'm going through that really fast, and you can do each of these in any order. And the information that you would get from the mass spec So underneath here, I know there's a molecular weight of 74. And so now I would just map backwards and I would say, how many carbons could I have for just 3 of those? Now, if I've already looked at my other spectra, I know there's 1 oxygen. So I'm going to subtract 1 oxygen. If I didn't know that, I would have just started with carbons. So 8, 6. Okay, so now I have 58. So how many carbons can go into 58? All right, well, we could do 4. Let me see. So that would be 48. That would leave me 10. All right, this is an even number, and that would be the remaining hydrogens. And then I'm just going to check. I'm going to say C4H10O. Does that make sense? So let's check our units of unsaturation. 2 times 4 plus 2 is equal to 10 minus 10 is 0. So that would mean there are no pies and no rings. But if we have already looked at the spectra, we know that there's a carbonyl. So that cannot be our formula. So we go back. And oh yeah, carboxylic acids have 2 oxygens. And remember, the mass spec is basically the plug and chug way. It's more of an art than a science. All right, so if I have my 2 oxygens, I'm left with 42. So that will accommodate 3 carbons. And that leaves me 6 hydrogens. So that gives me C3H6O2. All right. 2 times 3 plus 2 is 6, 7, 8. And I have 6. Remember, oxygens don't count in the units of unsaturation. 2 divided by 2, that is 1 unit of unsaturation. So I get 1 pi or 1 ring. And that matches all of my spectra. So that is my molecular formula. All right. That was a whole bunch of information very quickly. But remember, each of those pieces have their own handout with lots more details. All right. That concludes the review of the structure and the spectra for the first semester. Okay. Until next time, jolly out.